Okay, so on your green packet on solving similar triangles, you read in the handwritten instructions at the top. What does it say? What are the handwritten instructions? Circle the required, the non-zero extra credit. This is the way to start off the fourth term of some extra credit. And you should consider that. We're going to jump over to the back side number 15. And for this to go out, your camp on similar triangles out. We learned 3 ways to solve triangles are similar last time. Now, the difference in congruence. No. No. Stand up or sit in your chair normally. I didn't hear what you said. Okay, there are 3 ways to prove that triangles are similar. One is angle, and we underline that angles have to be, what do we underline? 2 angles have to be congruent. Side. So side is different than triangle congruence. These sides are not congruent, but 3 corresponding sides are, what's the word we underline? Oh, starts with a P. Come in and do your brush. It starts with a P. Starts with a P. Proportional. Okay? And last one side, angle side, the angles congruent, the sides are proportional. I need a volunteer. You're not going to do anything other than just volunteer. Okay, Connor, thank you. Connor, what's your last name? Hold on. Oh, here is Connor. Who else? Hunter. Okay. Yep. Okay. Thanks, Hunter. Here's Hunter. What? Hey, currently, these are both congruent and similar. Congruent has a symbol. What do we use when she did that congruent? Equal, which means they're equal, and the squiggly actually also means that they're similar. Because the tilde means similar. So these 2 pictures are similar, even though they are also congruent. They have a 1-to-1, they're proportional 1-to-1. Now, watch what happens when I go to a corner. Probably. What happens to the angles? They stay the same. So again, the reason why the angles are congruent, but the sides grow proportionally. The sides grow proportionally. The angles stay congruent. So when we use our postulates on congruence, angles are congruent, the sides are proportional. So let's look at number 15. It says state if the triangles are similar. So we have to explain which one of these. So they're all going to calculate. We don't look at one. Do not throw that. I don't guess that. But it's on the softball team. And then throw it under hand. Hey, Connor, sit down. Okay. you shouldn't throw the pencils. Stop. Hunter, stop. Stop. Okay, we're on number 15. Say that they are similar. If so, say how you know they're similar and write the similarity statement. Okay, so we have the proportion. We have, again, two types of triangles. We have the small triangle, and we have the large triangle. We also have two other categories. Our small triangle, do we know all sides of the small triangle? No. So the ones that we can't use in our proportion. We can choose the other side as long as the big side, the big triangle has our diagonal on top and the right diagonal. Do we have lengths of both of those? Yes. We know the length of this side of the right triangle and we know the length of this side. So we can choose to use either one. Let's use the left diagonal and left diagonal, and we know the right diagonal. We can't use the base because we don't know the base of the smaller triangle. So, just like our last story problems, is fill in the blanks. Do we know the left diagonal length of the small triangle? Do we know this length of the small triangle? It's 41. So, what's the large triangle's left diagonal? From here to here. Yeah. I don't see 112 type there. Where did you get 112? Yeah, we have to add these together. So in total, it's 112. Okay, the right diagonal. Well, the smaller triangle, how long is that on the smaller triangle? 29. And on the right triangle, how long is that? 80. Now, if these are actually similar, then they should have a relationship from small to large, where they are growing and shrinking at the same rate. Also, the side lengths, the left diagonal to the right diagonal, should have the same relationship, whether it's on the small triangle or the large triangle. So what we're going to do is simplify both the fractions. If they simplify to the same simplified form, then they are similar. If they don't, they are not. So, everyone, every calculator, open it up. Type 41 divided by 29. You know how to simplify a fraction on a calculator? If it is, you get a decimal. You hit math. Where's the fraction once you hit math? Number one, you actually go math. Enter, enter. What's the simplified fraction? 41 over 29. Math, enter, enter. So that one was already in the simplest form. We need to do it on the other side as well. Type 112 divided by 80. Math, enter, enter. 112 divided by 80. Math, enter, enter. Okay? Sheldon, what did you get when you simplified the right ratio? 112 divided by 80. Math, enter, enter. What do you get? Enter, enter. Do 112 divided by 80. Oh, you know the answer. We don't need that. Do 112 divided by 80. Not enter, enter. There you go. What do you get? Question number 5. Do these equal each other? Are they the same? No. So are these two triangles similar? No. They're not similar. The only thing they have in common is one congruent angle down here. The sides are not proportional. So it fails the side angle side. And the sides are not proportional. So we say no, because the sides No, because the sides are not proportional. Okay, that was one of the required ones, I believe. You flip it over to the back, I think it's number 19, we're going to do that one too. This one's an extra credit one. Oh, that's if they are similar, then you would write the similarity statement. But we gotta know, so we don't fill that in. Okay, number 19. Okay, number 19, we need to pick two of the corresponding sides. We know the categories is we have a large triangle and we have a small triangle. Now there are two of the corresponding sides. H what? HF and, yeah, the tops, right? So we have the top. What's another pair of corresponding sides? How do you know those? One's on the left and one's on the right. How do you know those are supposed to go together? We have to flip this one around so that it's going in the same direction. So F, H, G. The longer side is 60, the shorter side is 30. 65. So we flip it around, now they're all going the same direction with the longer side on the left. Okay? So we can either use KL, the 96 and the 60, or we can use the 48 and the 30. Since we know the measurements or the lengths of both, that's our choice. Which one do you want to use? 48. Okay, so I'll do the right side. Yeah? So let's label it right. And then we set up our proportion. Okay? Then I had you know the top of the large triangle. 104. Yep. Connor, we know the top of the smaller triangle. 65. Isaac Gilson, what's the right of the large triangle? And Isaac Nielsen, what's the right of the smaller triangle? 30. So notice none of them are missing. Don't have a variable. So our job is to simplify both and see what we get. So in with your calculators, 104 divided by 48. How do we go to a simplified fraction? Math, enter, enter. Isaac Sherman, what do you get there? We simplify 104 over 48. 13 over 6. Equals, what about 65 divided by 30? Also 13 over 6. So since they are equal, what can we say? They're not congruent, no. They are similar. The equals are congruent because they're similar. And the sides are proportional. So we're trying to similarity statement using what you saw Annabelle on the last one. When they're similar, they're actually going to use that. So we say yes. Triangle, KLN, if the two of them are similar to triangle, not triangle, then we have to make sure we get those letters in the right order. What angle corresponds to angle K? F. When we flip it around, you can see that right here. K and F. What angle corresponds to angle O? G. L is down here. And I can put congruent because angles are congruent even if the figures are similar. Okay, and lastly, N. You have to get those in the right order. I took it off the wrong triangle, you're right. H. Okay. That's how you do those ones. Let's go to the back side. Try one of your extra credit ones. Maybe page 29. Flip it over to the very back. Okay, solve for x, and you are told that they are similar. What type of angle is here? Angle TUS and angle LUK. What type of angles are right there? They're angles. So are those congruent? Yes, they would have to be congruent. Those angles are congruent. Okay, I should also know that because they're similar, and all corresponding angles are congruent in similar figures. Okay, so we need to find x. We need to find x. We need to set up a proportion. We have two triangles, right? We have the left triangle and we have the right triangle. Can we make a ratio of information with the left triangle? How, Johnny? Please don't be pushing that button all the time. I can buy me a new one. Can we make a ratio? Do we have two different sides we know on the left triangle? What do we know, Johnny? I think look at the left triangle. There are two different side lengths marked. What are the numbers? On the left triangle. The left triangle is this triangle. 30 and 40. Okay. Now, make sure you set up the second ratio in the same way. That should go on the top. Notice 30 is longer, 40 is shorter, 40 is longer. What's the shorter side? That should go on the top with 30. That's 6. And the longer side should go with the 40, because 40 is longer. So 2x minus 2. Now, before you start cross multiplying, you need to put in parentheses somewhere. Where should you put parentheses? Around the binomial. Otherwise, when you cross multiply, many of you are going to get the wrong answer because you won't times the 30 to both. So when we cross multiply, it is 30 times the binomial, 2x minus 2. Okay, and then now we'll go on the other side. Good, 40 times 6. Now I know 6 times 4 is 24, so that's 6 times 40. Good job, 240. Okay, then how do I multiply these two together? Let's start with a D. What? Don't fish another. The fishing, oh. Extremely properly. Okay, and then we'll put both of those in. Gauge, what do we get? Good. And if you bring the parentheses, a lot of people will say minus 30. Or minus 2, actually. They'll say minus 2. So make sure you remember the parentheses, because it was minus 60. So we add a 60 over. That comes out nice and pretty. 300. 60x equals 300. Which should be right. Divided by 60. The zeros cancel out. 30 divided by 6 is 5. Okay? So the evens are required, or not evens, sorry, the circled ones are required. The other ones you can earn yourself some extra credit. And you can have some time at the end. Okay, now, Isaac Nielsen, would you help the light back there in the middle right, please? Yep. Okay, we're going to move on to dilations. Now, when in the real world, I can see that many of you that have had this before, in the real world, you have experienced dilations. Your pupils, because who's been to an eye doctor? I've been to an eye doctor once in my life. 20 was the first time I went to the eye doctor. And I was getting my prescription sheet, and I was leaving my parents' health insurance and eye insurance, vision insurance, onto my dad. So my mom's like, well, you've never been to the eye doctor. Maybe you should go before you're off for insurance. So I went to the eye doctor, and I experienced a weird thing. They dilated my pupils. I don't see pupils when they get dilated. They go there. And then I remember when I was in the car, during the car, I saw on my phone when I was stopped at a light. I wasn't driving, I was stopped at a red light. I saw on my phone that I had a missed call or missed text or something. So I went to look at it, I picked it up, and I was like, whoa, I couldn't see it. It was the first time I experienced blurry vision in my life. I was like, did the thing my parents do? Like, they try to like move in and out, trying to focus. What? No. Well, my parents wasn't around good vision, so I've never had to wear contacts or anything. I had eye drops in during grad school. Grad school, I swear, gives you health problems. My health problem I developed was dry eye syndrome because I never slept and I read a lot because I had to read all this research. And so I learned how to put eye drops in, but since I've never worn contacts, I'm not used to like touching my eye or getting really close to my eye. So you can just put eye drops, and you don't even have to like hold yourself down. You just go, and then yeah, I was like, people are holding their out, and I still blink, and then it just goes down my face instead of in my eyeballs. So really hard for me, so I put them in every day. So, anyway, dilations. There's a center of dilation. When your pupil changes, does it turn into a star or a heart? Is it still a circle? Yeah, and the center of dilation is in the middle, and it expands and contracts around the middle. The center of dilation, which for your pupil is in the middle of your pupil. Okay, so we're going to watch a short video on dilations. When you're quiet, we'll do that. When you're quiet, we will push play. Thank you.
Understanding dilations. In math, dilation refers to the process of making a polygon larger or smaller without changing its shape. It's picture day. Kate chooses the package with one photo for her parents, a larger one for her grandparents, and smaller photos for her friends. How can photographers print one photo in different sizes? Dilations. Dilation is where a two-dimensional shape grows or shrinks proportionally from a point called the center of dilation. Here we tripled the original rectangle. And here we divided it in half. In dilations, the dimensions and distances from the center of dilation stay in proportion. The center of dilation can be anywhere in, on, or outside of the shape. Scale factor determines how a shape grows or shrinks. If the scale factor is 3, the dimensions from the center of dilation are multiplied by 3. Different sizes, same proportions, same shape. A coordinate grid can help us see how this works. If the center of dilation is 0, 0, and the scale factor is 3, the horizontal distance from the center of dilation is 3, and the vertical distance is 4. Multiplied by a scale factor of 3, the horizontal difference becomes 9, and the vertical distance becomes 12, stretching the shape 9 units to the right of the center of dilation and 12 units up. Nice portrait, Kate. Grandma and Grandpa are so proud. If the scale factor is 1/2, the original dimensions are multiplied by 1/2. The dimensions of the reduced photo are 1.5 and 2. Different sizes, same proportions, with dilations.
Okay, great. So we have Hunter's picture. Here's Hunter's picture. Here's Hunter's picture. Where is the center of dilation? That's the place you like hold while you expand. So when I was doing this, where was his center of dilation? The top left corner. That's the point you hold constant. Can you sit up, please? and then the rest of them expands and contracts, right? But I think Nelson, can you turn the light on, please? So, took one of these on dilations. Pass one of them to Connor, please. As I said in that short video, everything grows or shrinks by the scale factor from the center of dilation. So it's important to know where the center of dilation is. Emily? Okay. So dilation is has a center and scale factor with a parallel line and line segment. Let's skip to the bottom actually, so we know that since you already have the video. Example 1. A prime, B prime, C prime is the dilation. So that's the one that's been changed. It's not the original. No. Okay, ABC is the pre-image, or the original image. So that would be right here. Okay? Point O is the center of dilation. Is the center of dilation on the actual original triangle? No, so it's not quite like Hunter's picture because his center of dilation was on the top left corner. We just pull that and then pull the other side and it grows and shrinks. It doesn't really move around the page. So when the center of dilation is not on the actual figure, then it's going to move around a little bit as it's growing or shrinking. Okay, with a scale factor of 3, well, AB was how long? 2 of the original. So a scale factor of 3 means everything is being multiplied by that scale factor. So 2 times 3 means our new image will have a height of 6. 6. And its distance from the origin, which is our center of dilation, has also grown by multiplying by 3. Okay, the width from B to C, B was at, let's see, x equals 1, C was at x equals 5, so how wide is that? 4, and I got those from here. B was at x equals 1, C was at x equals 5, so it is 4 units wide. Well, if we use a scale factor and dilate it by a scale factor of 3, 4 times 3, 12. So that should be 12. Well, B prime, it says is that x equals 3 to x equals 15. Is that actually a distance of 12? From 3 to 15? Yeah. And maybe you can put that in to do A to C, but we're not going to. Okay? Let's look at example 2 and dilate the triangle. This one's really nice too because the center of dilation is actually on the triangle. So, using the graph, we're going to draw our triangle A of 0, 0. So go to the origin, go to point, and put A. Plot it, please. B is 4, 0. 4, 0, remember, means they come on the x-axis. 1, 2, 3, 4. Label that B. And C is 4, 3. So 4 over, 3 up. C, and connect them, and there's a triangle. Okay, we're going to stuff here and here and all the other. Put this in your bag. Okay, we're going to increase by a scale factor of 2 with a center of dilation at the origin. So we're going to hold down A, and we're going to increase the triangle with a scale factor of 2. So if this length was originally 4, how long should the new length be? 8, because it's multiplied by 2, right? So 4, 5, 6, 7, 8. So it gets elongated out here to 8. So that will be B prime. A little apostrophe or tick mark is B prime. That's our new B. Now B to C was originally a length of 3. So we're going to go straight up to 6. 4, 5, 6. And that will be C prime. And we connect A to C prime to B prime, we have our new dilated triangle with a scale factor of 2. So SF was 2, scale factor was 2. Let's look at what happened to the area. What's the area of a triangle? Okay, but what's the formula? That's for a line. Area of a triangle. 1/2 take the earbud out, please. 1/2 what? How many, okay, what if you're doing a rectangle? What's the area coming in a rectangle? Base times height. For a triangle, there are 2 triangles. So a triangle represents half of a rectangle. So 1/2 base times height. 1/2 base times height. And that's a formula you should have memorized. Base times height over 2, you can write it that way as well. Yep. Okay, so let's do the area of the original. That little O is to remind you that's the original. So 1/2, we need the base and the height. Fingers in the air, what's the length of the base of the original triangle? Fingers in the air, that's a smaller triangle, fingers in the air. What's the length of the base of the original triangle? Thanks for those participating. The rest of you should be able to look at the base and figure out how long that is. Remember how long is that from A to B? 4. Okay, now we need the height. Fingers in the air, please, everyone. What's the height? Put it up in the air of the original triangle. Good. 3. Good. Okay, so 4 times 3 is 12. Divided by 2 is 6. Okay, now let's look at the area of the dilated. I'll put a D for dilated. The new image. 1/2 base times height. 1/2 base times height. Fingers in the air, that's the base of our new image. Thanks, Gerardo was first up, I think. What's the base of our new image? Okay, that was from here to here. From A out to C, how many units is that? 8. Okay, I almost saw 7 fingers. 8. Okay, as Wilson, how tall is that? What's the height? What's the height of our dilated triangle? 6. Okay, 8 times 6. 8 times 6 is what? What's 8 times 6? 38 divided by 2. 24. So when the sides all doubled, the area doubled. 6 times 2 is about 24? No, that's the area. It quadrupled because we're doubling the length and we're doubling, I guess this is the width, we're doubling the width and we're doubling the length. We're doubling it in 2 directions. And once we get area, everything's squared. So our area is being quadrupled because your scale factor squared is your relationship to the area. For the area, you take your scale factor and you square it. So in our case, it was 2 squared, which is 4. So the area quadrupled. quadruples. Okay? All the lengths double, but the area was quadrupling. What if our scale factor was 3? What happens to the area? What's 3 squared? 9 times as big. I don't really have a word for that. After quadruples, I don't know what you call it. 5 times as big, 6 times as big, up to 9 times as big. Okay? So, flip it over, please. Let's look at the next page. Okay, dilate. This is up here, there it is. Dilate the triangle vertices A, B, and C. So first thing you need to do is plot the vertices. Plot A, B, and C. And label them. A is 1, 1. Find where 1, 1 is and plot it. And label it A. B is 4, 1. 1, 2, 3, 4. And label it B. It's really nice when sides are perfectly horizontal or perfectly vertical from each other. When you get to diagonals, you have to go into Pythagorean theorem or distance formula a little bit. C is 4, 4. 1, 2, 3, 4. And then connect them so you have a triangle. Okay, this is dilate the triangle by a scale factor of 3. And this time, what's the center of dilation? 0, 0. So our center of dilation is not on our triangle. Right here is our center of dilation at the origin. Okay, now if our center of dilation was point A, we would just extend B prime out to the right a little bit. But it's not there this time. The distance from the origin up to 1 has to also be tripled. Let's talk about the length. A to B is originally how wide? How much? 3. The gap. 1, 2, 3. So if we have a scale factor of 3, it now needs to be 3 times 3 makes 8. A prime B prime has to be 9 units. Okay, now this is diagonally up 1, the distance from our center of dilation to here, diagonally up 1. So how many units do I need to go up diagonally from where A prime starts? 1 times our scale factor, 3. So I'm going to go diagonally from corner to corner, 1, 2, 3. A prime should start there. It's shifted. And then we'll extend out 9 units. So 3 times 3 was 9. One, 2, 3, 4, 5, 6, 7, 8, 9. So that would be B prime ends up being on the point 12, 3. A prime ends up being on the point 3, 3. So our triangle has been shifted a little bit. It's not only stretching, but it's moving because our center of dilation is in a different position. Okay, where would C prime be? What? 9 units up from B, that's a good way to explain it, because B to C is 3 units, and we already have B's locked, B prime's locked in position. So we take 3, multiply by the scale factor, and get 9. So if I'm on height of 3, I should end up on a height of 12. I don't want to go too high. What? No. But I'm on 3. 3 plus 9 is 12. Yeah, it's 12. 2 plus 9 is 12. So it would be on 12 comma 12. That would be our C prime. What? Did I only do 8? 1, 2, 3, 4, 5, 6, 7. Oh, that's weird. Why is it like that? Let's erase my line. Well, don't go all the way up to 14. That's too much. Okay, so C prime 12 comma 13. Huh, that's weird. Okay. Let's look at the area really quick. The area originally 1/2 base times height. Recall what was the base of the original and the height of the original triangle. And both 3. Okay, so 3 times 3 is what? 9 divided by 2. What's half of 9? 4.5. So, let's make a guess. Knowing the scale factor is 3, what should the area of the new triangle be without using 1/2 base times height? How do you get 40.5? I think that's times, is that times by 9? Okay, so our scale factor is 3, we square it, which means the area should get 9 times larger. 4.5 times 9. Yes, 40.5, you're right. And to make sure it actually works, our base here is how long? And the height? 9. So 1/2 of 81, because 9 times 9 is 81, is 40.5. So it worked. Okay, scale factor. And guess what would happen if we did volume? Because the area was growing in 2 dimensions, widthwise and lengthwise. We had to square the scale factor. Volume grows in how many dimensions? 3 dimensions. So we have to take the original volume and the new volume, we take the scale factor and we cube it. And it will grow that much by the volume. Okay. So now we have parallelogram. We also have triangles. Example 4, dilate a parallelogram. We just went over parallelogram stock. One property about diagonals. What do diagonals do on parallelograms? They bisect each other. 2 things about the angles. Opposite angles of a parallelogram are. That is what a parallelogram spot. It was a little big newspaper that we see from the corner. Opposite angles are. If you were here, then you have a video to watch on my website. Opposite angles of parallelograms are congruent. CIA angles in a parallelogram are, Hunter, you need to pay attention. CIA angles in a parallelogram are, no, they are supplementary. And there are 2 things about the sides. Opposite sides are the parallelogram. What's that first part of the word tell you? Parallel. And opposite sides are congruent. So when we draw a parallelogram, I have to actually make sure that it looks parallel, and the top and bottom and the right and left should be congruent to each other. So find negative 4, 4, and plot the point. Negative 4, 1, 2, 3, 1. 1, 2, 3, 4. So that is point A. Point B is at 6, 6. 1, 2, 3, 4, 5. There's 6. And 1, 2, 3, 4, 5. 6, 6. That 7 represents the very top of the screen, and the -5 represents the very bottom of the screen. Are you raising your hand? What? No. So C is 6, -2. So right 6, down 2. And D is -4, -4. So left -4. Oh, okay, so this one's D. Sorry, the mouse was over it, so I couldn't see it. -4, 6, and 4. That's better. Okay, and you connect them, hopefully with straight lines. Are those two sides congruent? They're right. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. They are congruent. And parallel because they're perfectly vertical. And those would also be congruent and parallel because it's a parallelogram. Now, they want to give a scale factor of 1/2. Does that mean it's going to grow or is it going to shrink? It'll be shrinking. Ooh, before I get too far into it, let's think about the area. If the scale factor is 1/2, and we use scale factor squared, what is 1/2 squared? What's 1 squared and 2 squared? 1 squared is 1, 2 squared is 4. So the area should be 1/4 the size, not half the size. The area is 1/4 the size. So it should look about 25% of the original. You can't make it because we're still in the middle of the problem. Okay, so at our, oops, I can't see it. Our center of dilation is at the origin, 0, 0. Okay, that's the center of dilation is at the origin. It doesn't have to be in the center. They've used things on the end, but that's what you hold down when you dilate it. Okay, so we need to know how far away each of these points are from the center of dilation. How do we find, actually I'm going to do a dash. How do we find that distance? What type of triangle is this? A right triangle. This is what part of it? Please sit down. No, don't sit down. It should get surprised. It says on the wall. Please see only with permission. Okay? What side of the triangle, don't you dare, you're cleaning all my desks. What side of this triangle is this dash side? So the right triangle, what side is the dash side that's across from the 90-degree angle? Starts with an H. It's called the hypotenuse. We can find the hypotenuse using a squared plus b squared equals c squared. So we want, the hypotenuse is just c. This is the distance formula. Square root of a squared plus b squared will equal that distance, c. Okay, so that distance should also be growing or shrinking by our scale factor. A is one of the lengths, the width. How wide is that from there to there? From 0 to -4, how wide is that? No, length is negative positives. So we have 4 squared plus, how tall is the triangle? 5. Nope, you're right, it was 4. 4 squared. So we have 16 plus 16, which is what? Square root of 32. Square root of 32. Then this square root of 32 just doesn't come out very pretty. So, you can also see this visually, because look at what happens if we go down 1, right 1, down 1, left, sorry, this is left. Down 1, left 1, down 1, left 1. We can use the same idea we did on the last problem where we just looked at the diagonals. There were essentially 1, 2, 3, 4 diagonal boxes. Okay, if we times that by our scale factor 1/2, that's 4 times 1/2. 2, because timing by 1/2 is the same as dividing by 2. So our new D is going to be right here, D prime. So I went down 2 diagonals. What? Yes. Okay, look at A. Does A go up 1, left 1 perfectly? Up 1, left 1, up 1, left 1, up 1, left 1. Okay, so how many diagonals do we need? 1, 2, 3, 4. You can flip up 1, left 1. So if we divide that by 2 with our scale factor, where are we going to be at? What's 4 divided by 2? 2. So I should be right here, halfway. Ooh, halfway, because the scale factor is halfway. Okay, that's A prime. Same with the B. How many diagonals does it take to get up there? Up 1, right 1, 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 up 1, right 1. How many was that? 1, 2, 3, 4, 5, 6. So half would be 3, or half the distance. So our B prime would be right here. Same with C. Okay. Now, so C, we know A to D was, and A to D had been shrunk by a half. Let's make sure that works. A to D was originally how tall? 1, 2, 3, 4, 5, 6, 7, 8. Is A prime, D prime now 4? So here, is that now 4? Yeah, Johnny, sit up. Okay. And our B went up 1, right, 1, 2, 3, 4, 5. So this would be the same, up 1, right, 1, 2, 3, 4, 5. Which actually makes sense because B to C prime has to be half the length of B to C. How long is B to C? 8. So B to C prime is 4. Okay, so there is our dilated, and I'll change the color now. This is the new dilated, and it's 1/4 the area of the original. Okay, so measure the side lengths to make sure they are proportional. We already did that. Okay, we're going to say that it's now 75% smaller. Right? Because the area is 25% the size. Okay, I think that's the end of the packet, yes? Alright, so next time due is your yellow story problems on similar triangles. The homework tonight that we'll answer questions on next time is on the green packet, all the circled ones. And, yeah, I'm going to go on the sentence. Let's try not interrupting. Please sit down. Pick up the lid of the calculator and the pen down there, please. Not under my permission. Okay, sit down. Sit. I'm almost done. Go in the purple box. No, I'm still in the middle of the sentence, guys. Stop trying to interrupt. Wouldn't be so long if you keep interrupting. Again, your homework, you next time is to go over the story problems on the similar triangles in this yellow. Next time we'll be answering questions on the yellow dilations and the circle problems on the green packet. Does that make sense for your homework? Okay, so you need to pick one of those for the rest of the class and work on them. These are those out here now, Isaac. Okay, I would probably choose to do your story problems first to make sure that's completely done on time. Yeah. You can work on the story problems. Yes or no? Then you need to work on the other assignments. I don't even see you sitting down. If you need help, you would sit down and you would raise your hand. I have answered that twice.